Good morning. This is another video of the second unit, Descriptive Statistics, and in this video I will talk about parameters of dispersion and shape. In the previous video I talked about parameters of position, but these are different parameters. And in statistics, one of the most important parameters of dispersion is called the variance. The variance is defined according to this formula. Okay? Approximately, it is like the average of the squared deviation with respect to the average. Okay, this is important to understand the concept of the variance. Once again, if we take a look at the formula, okay, so more or less, so we're summing something and dividing more or less by n, so it is more or less like the average of squared deviations with respect to the average. It is not exactly the average. Instead of dividing by n, we divide by n minus 1. So the reason why we make this is not easy to explain. We will explain this further in the unit of inference. Now, the notation that we are giving to the variance is s squared. This is because we work with n values and we assume that those values correspond to a sample. If instead of the sample I'm working with the total population, usually we call it sigma squared. Okay, this is the variance, and so this is not easy to explain why we divide by n minus 1. Okay, this will be an issue of a future video. What is the standard deviation? The standard deviation is just the square root of the variance. This is a very, very important rule in statistics. Okay, then what are the units of the variance? So for example, if I have values in centimeters, imagine that I ask the height of people in centimeters, so the units of the variance will be centimeters squared. If the values are in minutes, the units will be minutes squared. But in the standard deviation, as I make the square root, the units will be the same as those units for the data. Okay, and this is what I was saying. If my data correspond to a sample, the variance is s squared, or the standard deviation s, but if the data correspond to the total population, instead of s squared, it is sigma squared. Sigma is a Greek letter. The standard deviation is just sigma. So another parameter of dispersion is called the interquartile range. By definition, it is the difference between the third quartile minus the first quartile. Okay, this is a very interesting parameter. I will talk now about the advantages. The range is much simple. The range is just the difference between the maximum minus the minimum. It is called the range. And now another coefficient, another parameter of dispersion is called the coefficient of variation. It is the ratio between the standard deviation divided by the average. The advantage of this is that it has no dimensions. So we can change the dimension and the value does not change. So which one is more robust in the case of outliers or in the case of skewed distributions? Okay, this is a very good question. The range is not robust. Okay, imagine that I have an outlier. Okay, so the range is obviously much affected by that outlier. Imagine that if a value is very, very high and it is erroneous, the range will be much affected by that outlier. And also the variance. So if I have an outlier which is much, much bigger than the rest, and we should remove that outlier, okay, it affects a lot the variance. But it does not affect the interquartile range. Okay, if you remember the concept of the interquartile range, okay, so third quartile minus the first quartile. The third quartile is the value so that below I have 75% of the values. So that if I have an outlier, it does not affect the calculation of the quartiles. So we say that the interquartile range is robust, is recommended in case of outliers or in case of skewed distributions. For example, if I want to compare the dispersion of skewed distributions, this is one option. Okay, well, now I'm going to propose you with an exercise. what is the interval of the values if the average is 10 and the range of 6? Well, so let's assume that this distribution is symmetric. Let's assume that it is normal. So we can say 10 plus minus 3, so between 7 and 13. So more or less, we can think that between 7 and 13 will be the range of my values. Okay, so if I have the average and I have the range, I can know more or less the minimum and the maximum. So it is very useful. But what happens if I have the average and I have this standard deviation? Is it also possible to guess or to have an idea about the minimum and the maximum? Well, the answer is yes. So, but for this, we have to assume a particular kind of distribution. So in practice, the normal distribution is very common. So let's assume that we have a normal distribution. So this is a very important rule. So this is the average, which is the axis of symmetry. So if I take the range of values comprised between the average minus 1 times the standard deviation and the average minus the standard deviation until the average plus the standard deviation, so that comprises 68% of the values, which is more or less like 2/3. But if I take the range between the average minus 2 times the standard deviation until the average plus 2 times the standard deviation, that comprises 95% of the values. And this is one of the most important rules in statistics. So in this subject of statistics, this is maybe one of the most important rules. The average plus minus 2 times the standard deviation corresponds to 95% of the values, which is most of them. In statistics, when we talk about most of the values, in many cases we talk about 95% or 99%. Okay. For example, there's a unit that we will talk about 95% confidence interval. Okay, it's very used in statistics. What happens if I obtain the interval of the average plus minus 3 times the standard deviations? Well, in a normal distribution, it accounts for 99.7% of the values, which is nearly all of them. Just 3 out of 1,000 will be outside this range. Okay, so this is nearly all of them. So this rule is used very often in control charts used in the industry. Okay, so now based on this rule, so we can answer to this question. So we can use this rule, the average plus minus 2 times, and guess more or less about the minimum and the maximum. Then another interesting idea is, what is the range of most common values in a normal distribution if the average is 0 and the standard deviation is 1? So we apply this rule in the center, and it is between minus 2 until 2. Okay, so now remember that we have parameters of position, parameters of dispersion, but also we have parameters of shape. Okay, and one of the most important is the coefficient of symmetry, also called skewness coefficient. This is the formula. Okay, the formula is non-dimensional. So, for example, if the unit is in centimeters, finally it has no dimensions. So, if we have data from a symmetric distribution, for example, a normal distribution, if we apply this formula to those data, we get a value of 0. Okay, but if we have a distribution like this, okay, if we apply this formula to those data, we get a coefficient of symmetry positive, and for that reason we call this as a positively skewed distribution. In those cases, remember that the average is higher than the median and higher than the mode. But if I have data from a distribution like this, if we apply the formula, we get a negative value, and this is why we call it as a negatively skewed distribution. Okay, then there's another parameter called the standard coefficient of symmetry. We just take this value and then we divide by the square root of 6 divided by n. So this is like a slight correction that we apply to this coefficient. But it is an advantage because if we apply this formula, so it follows a normal distribution with an average of 0 and the standard deviation of 1, okay? It happens with the number of values is more or less higher than 150. And remember that in those cases, the usual range of values is between -t and 2, okay? So it is very often. So if the coefficient of a symmetry or a skewness coefficient is outside this range of -2 and 2, we can conclude that it is a skewed distribution. But if my value is comprised between -2 and 2, we can say that it is a sample extracted from a symmetric distribution. Good. So there is also a useful coefficient that provides information about the shape of the distribution, which is called the kurtosis coefficient. This is a formula. The formula is similar to the previous one, but now instead of a value 3, we have here a value 4. Okay? It is also non-dimensional. Okay, so very often we subtract the value 3, and now I'm going to explain why. Okay, so if I have data from a normal distribution and I apply the formula up to here, I will get the value 3. And then obviously if I subtract this value 3, it becomes 0. This is why in many books or in many statistical softwares, this value 3 is also applied. So based on the kurtosis value, we can, if the distribution is symmetric, more or less something like this, I can have 3 possibilities. The normal distribution corresponds to this curve in color orange. So the blue curve is similar to the normal, but like more pointed, more sharp. It is called leptokurtic distribution. But I can have a distribution which is more flat than the normal. It is called a platykurtic distribution. Okay? So the normal distribution is called mesokurtic. Okay? So this kurtosis coefficient is very useful in case of symmetric distributions. If I have a symmetric distribution and the shape of the histogram more or less resembles like a normal, okay, so it is very useful to check the value of this kurtosis coefficient. If the kurtosis is positive, I will say that it is a leptokurtic distribution. For example, it is the case of the student T distribution. And if it is negative, I will talk about the platykurtic distribution. For example, it is the case in a uniform distribution, or in the case of the mixture of two populations, or even it may happen in the case of outliers. Okay, well, again, we can also have the standardized value for the kurtosis coefficient. So we take the value of this coefficient and then we divide by the square root of 24 divided by n. So again, it is like a slight change in the formula, but it becomes very useful because if the number of values is large, so this coefficient follows a normal distribution with an average of 0 and the standard deviation 1, which means that the range of values, most of the values are comprised between -2 and 2. Okay, so based on this, so if the standardized value of the kurtosis coefficient and the skewness coefficient are comprised between -2 and 2, okay, we can say that it is a sample extracted from a normal distribution. So this rule is used quite often in statistics to identify if the distribution can be considered as normal. Okay, well, so here I finished this unit about dispersion and shape parameters. Thank you very much for your attention.